it is possible for a spherical object, maybe like a fish bowl filled with water or a spherical bowl filled with water or something like that, to produce images. And we're going to look at the equation that goes along with that. So the equation is n1 divided by the object distance plus n2 divided by the image distance is equal to n2 minus n1 divided by the radius of curvature of your object. So let's take a look here. So let's say I've got a spherical object like this, and it's got a squaring out at this side here. I've got an object here with light coming off of it. A light ray incident upon this surface will get refracted in to a point. Light coming off here gets refracted to that point, and light coming this way gets refracted to this point here. Where those light rays intersect, that's where your image is going to be. So your object distance is the distance from your object to the edge of that spherical object. Your image distance is the distance from that edge to where your image is actually formed. And your radius of curvature is from the center of your object's curvature to that edge that is curved. And let's say this is an object that has water in it, so n inside here is going to equal 1.33. And let's say we start off with an object distance of 40 centimeters. And we're trying to figure out where this image is actually going to be made. Okay, so our object starts in air, so it's 1.00 divided by an object distance of 40 centimeters plus 1.33 divided by image distance, which we don't know, equals, now n2 is going to be inside, so 1.33 minus 1 divided by the radius of curvature. And let's say the radius of curvature is 5 centimeters. Okay. So now we need to subtract this. We have 0.33 divided by 5. And we need to subtract 1/40th over there as well. So we have 1.33 divided by image distance is equal to 0.041. And then solving for I, we get a distance of 32 centimeters. That'll be a upside down image, so in a real image, and you can use the same equations as before with magnification and things like that. So it all works the same as lenses and mirrors. But that's what you would see. If we have an arrow up here, like we do with the other diagrams, you'll have an upside down arrow there. Now let's go back to another thing that we've done before. Let's say I've got a block here filled with water, so n is 1.33 inside here, and I've got objects inside here. Maybe a fish tank would be a good example here. So let's say I've got a fish right here, and we have a person's eye looking here, okay, watching the image there. So there's a fish located at an object distance here. The image is going to be located about right here. And why would that be so? Well, let's trace a light ray coming off the fish here, coming out of the fish bowl. That one goes straight. We have a light ray coming here. It's going to get refracted outwards. Because remember, n is going to equal 1.00 here. This light ray hits here, gets refracted outwards. And the eye is going to be tricked into thinking that this light ray emerged from here. This light ray emerged from here. The one that went straight, okay, is good. So let's take a look at our equation. N1 divided by O plus N2 divided by image is going to equal N2 minus N1 all over R. Well, what's the radius of curvature of a straight line? Well, the radius of curvature is equal to infinity. There is no curvature of a straight line. So therefore this part, okay, goes to 0. So then I've got n1 divided by O plus n2 divided by I is equal to 0. Okay, and we can quickly solve for that. N1 divided by O equals a negative N2 divided by I. And that's our equation there. So if we know an object distance here, and we can quickly find our image distance, okay, based on the index of refraction of error being 1. So for our specific example here, we would just have 1 divided by object is equal to minus n2 divided by I. Okay, and n2 being 1.33 here. Okay, so that'd be a really easy equation that we can find for I. Essentially, what we end up doing is dividing by index of refraction of 1.33. So whatever my object distance is, my image distance will be 1.33 divided into that object distance if we're assuming water and air. So that's how it works. So if the fish is located in the back, it's going to look like it's a little closer, okay, to the front edge to the human eye. And I know you've looked in a fish tank before and kind of witnessed that. So that's how we handle images formed by either a spherical or a non-spherical substance that's inside of a glass container or some kind of container.